Hi, my name's Rayhan Alam, and I'm a sophomore student at UC Riverside.
My name is Alisha Wang, and I am a junior student at UC San Diego. Today, we want to talk about our research of our experimental evaluation of datasets in radio frequency machine learning, specifically with drone detections. As we all know, machine learning is such a hot topic in the field of computer science right now. In radio frequency field, we also utilize a lot of machine learning techniques in order to enhance the ability and classification methods and accuracy of RF signals. And our research specifically focused on drone detection. And why is that? Is because drones are actually a very important part of our everyday life. It is used in various circumstances from logistics to surveillance. Utilized two different RF datasets in our research, which are card RF and drone RF. The card RF datasets incorporate outdoor UAV and UAS drones with Wi-Fi and Bluetooth signals, while the drone RF datasets focuses on drone signals only. We replicated the classification methods of the drone RF datasets and implemented it on the card RF datasets. This evaluation will aid in developing a more robust experimental data collection and classification framework, improving the detection accuracy of radio frequency in drone detection. In the drone RF experimental setup, there are three essential parts. We have, of course, the drones, the flight control, which are mobile apps or physical flight controllers that are used to control the drones. And we have the RF sensing module that is a RF receiver connected to a computer. And on the computer, we have a program called LabVIEW that's used to store the data that we collected. Specifically, there are three different types of drones that we used in the drone RF experiment. They are the Parrot Bebop, the Parrot AR 2.0 Elite Edition, and the DJI Phantom 3 standard drone. And these three drones have various different type of dimensions, weight, capacity, range, and connectivity as shown in the table here. We used PCIe interface kit to connect the NI USRP 2943R RF receiver with the computer.
So the data collection process starts by turning on the drone being analyzed and connecting to it using either a mobile phone or a flight controller. If a mobile phone is used, we launch the mobile app to control the drone and change its flight modes. We verify the drone's connectivity by performing basic operations like takeoff, hovering, and landing. Once the drone's operational, we turn on the RF receivers to capture all RF activities. These signals are transferred to laptops using PCIe connectors. We then open the LabVIEW program, configure the parameters, and start the program to fetch, process, and store RF data segments. And once the experiment is complete, we stop the LabVIEW program. This dataset is organized into three levels. The first level records RF activities when drones are off and when drones are on. In the second level, we focus on Bebop, AR, and Phantom drones to train and evaluate the system's ability to identify them. Finally, in the third level, we tested the system's ability to recognize specific drone flight modes, including hovering, flying with and without video recording, and ensuring no obstacles were hit. Now, taking the MATLAB code from the drone RF paper, we converted it into Python and created the following graphs. In the first graph, the first figure shows RF background activities. The second figure displays Bebop drone RF signals while flying and recording video. The third figure illustrates Phantom drone RF signals when connected and flying. These show the differences in the RF patterns based on various drone types and flight modes. Next, we also generated the power spectrum graphs and box plots for the RF signals. The top three graphs show the average power spectra of the acquired RF signals, while the bottom three graphs represent box plots of the computed spectra. In the bottom left graph, Class 1 represents RF background activities, and Class 2 represents drones RF communications. In the bottom middle graph, Class 1 is for RF background, while Classes 2 to 4 represent Bebop, AR, and Phantom drones. Finally, the bottom right graph compares flight modes, where Class 1 is for background activities, Classes 2 to 5 are for Bebop's 4 flight modes, Classes 6 to 9 are for the AR's flight modes, and Class 10 represents the Phantom single flight mode. This approach allows us to effectively detect and classify drones based on their RF signature and flight modes.
For the card RF data collection process, we collect signals from 2 Bluetooth devices, routers, and 6 UAV controllers in an outdoor controlled environment. The collected signal is then passed through a 2.4 gigahertz bandpass and low noise amplifier used to amplify the bandpass signal. We also use a Keysight oscilloscope to collect and monitor the RF signal and trigger a threshold for signal detection above the background noise level to eliminate all background noise levels. After the signal is collected and initially cleaned, the signal will go through a pre-processing stage to prepare for further feature extraction. And the initial RF signal start point will be determined by the change point detection algorithm in MATLAB to remove any noisy part of the raw signal. The RF signal and then pre-processed using a single level Haar wavelet decomposition algorithm, which involved passing the raw signal to a set of low pass and high pass filters. The downsample of the low pass signals will then be used for feature extraction purposes. The card RF hardware list can be seen on the right with the signal sources as mentioned before. All devices are in 2.4 gigahertz mode. The collection antenna, signal amplifier, and specific oscilloscope setup is seen on the picture on the card RF hardware list on the right. For the card RF exploratory data analysis, we used the techniques mentioned in the drone RF papers, as well as exploratory analysis code derived using the drone RF code demos. We performed data analysis on the graph of the normalized waveform for each UAV signals and compared them with the normalized waveform of the corresponding controller signals. The 3 graphs below represent the signals from a BB running drone and 2 DJI drones, also as well as their corresponding UAV controller signal. The blue waves represents the UAV signal, while the red wave represents their controller signals. From this, we concluded that neither dataset utilizes RF chambers, which are typically employed to collect clean and noise-free signals. We would like to explore the implication and impact of this omission on the data quality. Additionally, drone RF relies on software-defined radios, while card RF uses an oscilloscope in the data collection process. We are unsure whether or not these steps are integral to that affects the data quality of our data set, but that is something that we would like to explore further on down the line. For our citations, our main citations are within the 2 given paper for drone RF and card RF. Thank you very much.